Hello everyone and welcome to lecture. Today's lecture will be about the directional derivative. The idea is that very often what we want to do is we want to figure out what the rate of change is of a multivariable function in a different direction than one of the coordinate directions. Specifically, maybe you want to go and figure out what the direction is going if you walk or if you move to the left by right and up by 2. So the idea is that we want to be able to figure out how to take a general multivariable function and put a direct number on this rate of change. So the rate of change of a function in a specified specific direction. And this is what the directional derivative is called. And we'll go over in this lecture how to figure out the correct way of calculating this value for any function. And we're going to focus on functions in 2D, so functions of two variables. But the formula that we get will actually be very general. It holds for functions of any number of variables. It's the directional derivative is something you can talk about in for any type of function of any number of variables. Now, the idea behind the directional derivative is that it's going to be based on something we've seen before coming from the chain rule. Specifically, we saw that if you have a curve, a parametric curve, so it's a curve that's parameterized by the following. You have x as a function of t and y as a function of t. This is in 2D, but again, it can be done and talked about for functions of three variables as well, as we saw in the chain rule lecture. So if we have a parametric curve, and we also have a multivariable function of each one of the variables of that parametric curve. So we have a function, say, of two variables. We saw that the chain of dependence, or the dependency diagram, the tree diagram, for this scenario give us the following. So if the output of the function, say, is w, you have that w is a function of x and y. It depends on x and y. But on the curve, for points on the curve, each one of these variables, x and y, depends on t. So when we go to, say, figure out what the derivative of w is along the curve, on the curve, or the derivative of the composition f of r of t, right, we ended up showing that this is the same thing as the gradient of the function f at the point on the curve, dot product with the velocity vector on the curve. And this expression gives us exactly the derivative along the curve tangent to the curve. So as for like a picture here, we can think of having an x-axis or y-axis. You have some curve or points on the curve are given by r of t. It's a position vector that gives us points along the curve as we travel along the curve. And what this is saying right here is that if you take the tangent vector to the curve, or the derivative r prime. We also call this, if t is time, we sometimes call r prime the velocity vector on the curve. That's this red thing is right here. This vector r prime is always tangent to the curve, and the idea is that as you move along the curve, we showed using the multivariable chain rule that the derivative of this function on the curve, or restricted to the curve, is the dot product of the gradient of the function at a point on the curve, dotted with that velocity vector, that tangent vector. So what this is saying is that this quantity right here, this underlying quantity, depends on both the gradient of the function, so the partial derivatives of f, but it also depends on this velocity vector, r prime of t. So the tangent vector to the curve. So the motivation behind the directional derivative is we want to, in some sense, use this idea, but remove the dependence on the velocity vector, because the idea is that what this is saying is that if you're moving faster along the curve, right, if your velocity is much more fast as you're going along the curve, that's going to make the rate of change along the curve of the function be much higher, which makes a lot of physical sense. Say, if you're moving in a temperature field, if this function f is a temperature, the faster you move through the temperature field, the faster you expect, or the higher rate of change you expect to see for the temperature function. If you're moving at a rate of 10 meters per second through a temperature field, you expect to feel a higher rate of change than someone who's moving 1 meter per second through that same temperature field. But for the directional derivative, what we want to do is we want to kind of remove this path dependency from this expression. We want to be able to just find a number, right, that tells us the exact rate of change of a function in a certain specified direction, without having to rely on without depending on how you traverse the path. Oops, and I just realized, I'm very sorry, I ended up forgetting to put the derivative symbol right here in front of this composition. This should be the t derivative of the value of the function composed with the curve that we're on. So we've seen this through the chain rule already, right? This is a relatively one of our basic chain rule formulas that we presented in the first lecture. But the idea is that we want to take this idea and use it to define the directional derivative, which is in some sense independent of the curve. It only tells us the rate of change of the function and the function alone in a specified direction. So this is the main idea for how we're going to kind of approach this directional derivative. All we want it to give us is a number that is a measure of just and only the rate of change of the function in a given direction. We want to remove the path dependency from this value. But just like the partial derivatives, this has a nice limit definition. We can very concisely write down what's called the limit definition of the directional derivative. And this is in order to do this, what we need as follows, we need to kind of draw a picture and get an idea of what exactly we're talking about. So we have our x-axis and our y-axis. We also need a point at which we're going to be evaluating the directional derivative. In general, we'll just kind of call this point r0. So this point right here is, we'll call it r0. So we need some point r0, which we'll call x0, comma y0. It's the position vector of that point. And then we also need a direction that we're considering the directional derivative in. And we always need that direction vector to be a unit vector. So we typically call this u hat, or u with a little hat over it. Remember, a unit vector means that the dot product itself, or its length squared, is equal to 1. This is important because we need a unit vector in order for this to not depend on the path of approach, or the path that we're figuring out the directional derivative in. So I'm going to put here again, u hat is a unit vector, or a vector of length 1. And then lastly, we need a function to differentiate. So we need some function w is equal to f of xy. Now again, it's important to note that the derivation and this limit definition hold in general for any number of variables. You can actually go through and do this for a function of 3 variables, of 4 variables. The mathematics itself is going to be very, very similar to the two-dimensional case, and the formulas that you get are also going to be very similar to the two-dimensional case, which I think is a very, very neat application and a very, very neat way of going through and defining this rate of change. It kind of, in some sense, the formulas that you get don't really care how many variables your function is. So the idea here is the following, right? We have some function f of xy, which maybe is a very high value over here. Maybe it has a very low value over here. And then as you move from, say, this point right here you'll kind of approach the lower value of the function. This is just kind of like a display showing the changing of the function gradually from this point right here to this point right here. So what we're interested in here is exactly the rate of change in the direction of this vector u hat. So in the direction of u hat at the point r0. Now you could do this at any different point here, but we want to figure out exactly how to do this. And the correct way of doing this is the following. You consider the line that stretches in the direction of this vector u hat. It's going to be the line that stretches, say, directly in this direction right here. Now if you move the direction of u hat, this line changes, but what we want to do is we want to figure out what the parameterization is of that line. I'll call it L of t for short. And you remember that to parameterize a line, This is from a previous Calculus 3 course, or a previous calculus course. Parameterization of a line is done by taking a point that the line passes through, in this case the vector r0, and adding to it the parameter t, say, we'll use t for our parameter, times the direction vector u hat. So I'm going to put an underline here under u hat as well, just to denote very clearly that this is a vector. So specifically, this gives us that x hat, or the x coordinate of any point on that line is given by x0 plus t times u1 hat, and then y0 plus t times u2 hat. So this is going to be an important idea when we go through and figure out exactly what the limit definition of the directional derivative is telling us when we write this down. So let's write this down, and we'll kind of interpret this a little bit. What we say is that the directional derivative, first off, the notation for the directional derivative is the following. It's, say, the directional derivative is capital D. You put a subscript of u hat to denote that you're taking the directional derivative in the direction u hat, and you're taking the directional derivative of the function f, and then lastly it's at the point r0. So this notation right here denotes the directional derivative of the function f at the point r0 in the direction u hat. We say that this is equal to the limit as h goes to 0 of the function value at r0 plus h times u hat minus the function value at r0 divided by h. And this is actually a formula that holds in general for any number of variable functions. This process actually works directly in 3D, 4D, any number of variables f can be. But in 2D, this is the equation. The limit as h goes to 0 of f of x0 plus h times u1 hat, comma y0 plus h times u2 hat minus f of x0 y0 divided by h. And this is exactly the exact definition of the directional derivative. So what is this saying? Well, if we kind of zoom in, let's zoom in around this point r0 right here and kind of try and show, an interpretation of what this is saying. This is saying that if this is r0 right here, and we go a very tiny distance away from r0, this point to this point right here, which is r0 plus h times u hat, this distance right here, if u hat is a unit vector, is going to be h. And what we're computing when we compute this limit is exactly the limit of the function at this point, this blue point right here, minus the value of the function at this black point, divided by h as h goes to 0. It's the normal derivative of the function, single variable derivative of this function, this composition of functions, in the direction u hat. So this is why this limit definition makes a lot of sense. And it's also why it is directly extendable to 3D or any number of dimensions. So the next thing we want to see is that this is in fact the same thing as the derivative of a composition. Right? This is the derivative. You remember the derivative of a composition of f with the line L of t. Right? This is exactly what this is, only it's evaluated at t equals 0, because t equals 0 gives you the point r naught. Right? L of 0 is just r naught plus 0 times u hat, which is equal to r naught. So because of that, the idea is that this derivative, the derivative of this composition, is exactly going to be, well, what this limit is right here. This is directly because of the fact that in the chain of dependence for the tree diagram for this scenario, we have that f depends on x and y, which also depend on t, where x is the x coordinate of points on this line, so it's x naught plus t times u1, and y of t is y naught plus t times u1. So this is the tree diagram for this. But because this expression right here is the normal single variable derivative of the composition of this function with the line, along this line right here, or along the line L of t, this expression, this limit right here, is the same thing as just this single variable derivative of the composition f of x naught plus u1 hat times t, y naught plus u2 hat times t, evaluated at t equals 0. Well, we know how to get this derivative from the chain rule. This is going to be the same thing as, and you could write it out shortly as the gradient of the vector times the velocity vector of this curve, the line. I'll go through this and do the chain rule directly using the procedure we talked about before, but just remember the simplified form of writing this in terms of the vector dot product. It's very, very helpful. This is going to be df dx times dx dt plus df dy times dy dt, all evaluated when t is equal to 0. So this is just going to be fx, the x partial derivative of the function f, dx dt on the line is just u1 hat. Df dy is going to be fy, the y partial derivative of f, times dy dt, which is u2 hat. This is all evaluated when t is equal to 0. And remember, t equals 0 is the same thing as r equals r naught. So it's the same thing as saying r is equal to r naught. So we can rewrite this expression a little bit more and see that this is the same thing as the dot product of the vector fx comma fy evaluated at the point r naught, vector dot product with u1 hat, u2 hat. Or in short, we can kind of say that this is the same thing. This is exactly equal to the gradient vector of the function f evaluated at the point r0, a vector dot product with the unit vector u hat. Right, and what we've just done is we've just derived a very, very nice and compact way for any function of determining the directional derivative. The directional derivative of a function at a point r0 in the direction u hat is exactly the gradient of that function, vector dot product with the direction vector, the unit vector that points in the direction we're looking at. So we'll see how to use this in a couple examples now. It's important to note as well that this formula holds directly for functions of multiple variables, more than 2 variables, so 3 variables or 4 variables as well. And the derivation is almost exactly the same. So let's try and find the directional derivative of the function xy e to the negative x squared plus y squared at the point r0 is equal to 1, 1 in the direction v is equal to negative 1, 2. So in order to use that formula from before, we have 3 main steps. 2 steps that we have to do before using the formula, and the last step is just the computation step. Step number 1 is to find the gradient vector. At the point r0. So this involves taking the partial derivatives. So we calculate df dx by taking the partial derivative of this expression, which we get, and we've calculated before, but I just want to go through and do this again so you get some practice. The x partial derivative of this is going to be y times, and you have to use the product rule, 1 times e to the negative x squared plus y squared plus x times negative 2x e to the negative x squared plus y squared, which results in the simplified form of partial derivative of f with respect to x is going to be y times 1 minus 2x squared times e to the negative x squared plus y squared. And then similarly, if you go through and calculate the partial derivative with respect to y, you will get the same answer. So you'll get it. We're just with x's and y's switched. I encourage you to go through and calculate that, or remember that this is a symmetric function of x. So because of that, we can use symmetry when calculating the derivative. And typically when we're calculating, we're not looking for the general directional derivative. We're only looking for it at a point. You can go ahead and look for the general directional derivative, and just kind of plug in, general points x, y if you want to. But for this function, for many functions, this would be a little bit too long to write down. It wouldn't be nice to write down. So I'm going to directly, before I plug these two things into the gradient vector, I'll go through and calculate exactly what they're going to be. If you do that, you get the x partial derivative at the point r0 is going to be the following. So we plug in the point r0, which is 1, 1. It'll be 1 times 1 minus 2 times 1 squared e to the negative 1 squared plus 1 squared. So it's going to be equal to negative e to the negative 2. And you get the same thing when you plug in for df dy at the point r0. So this gives us a gradient vector at the point r0 equal to its x component is negative e to the negative 2, and its y component is also negative e to the negative 2. So this concludes step 1 of this directional derivative calculation. Step 2 is to calculate the unit vector pointing in the desired direction. This is the direction that we're calculating the directional derivative in. So in this case, the direction that we're looking in, that we want the directional derivative in, is this direction right here. Remember that the unit vector is calculated for any vector in the following manner. If I want the unit vector u hat that points in the direction of v, I have to take the vector v and divide it by its length for the magnitude of this vector v. Remember, and you probably hopefully remember this from a previous calculus course, the dot product of u with itself, if you have this relationship, is going to be the same thing as the dot product of v over the length of v with itself, v over the length of v, which becomes the dot product of v with itself divided by the length of v squared. And the dot product of any vector with itself is just its magnitude squared, or its length squared. So that's equal to 1. So for any vector v, if it's not a unit vector, you have to do what's called normalize it and make it a unit vector by dividing by its length. So the length of the vector negative 1, 2 is going to be the square root of negative 1 squared plus 2 squared, or the square root of 5. So the unit vector that points in this direction is equal to 1 over the square root of 5 times the vector negative 1, 2. Or u hat is equal to the vector negative 1 over the square root of 5. This x component, and its y component is 2 over the square root of 5. And then our last step for doing this, calculating the directional derivative, is step 3, which involves just calculating the value using the dot product formula that we derived earlier. And this is done as follows. We say the directional derivative of f at the point r naught in the direction u hat will be the dot product of the gradient vector at the point r naught with this direction vector u hat, or the dot product of the vector e to the negative 2, negative e to the negative 2, comma negative e to the negative 2, dot product with the vector negative 1 over root 5, 2 over root 5. Which is equal to the sum of this times this plus this times this, which will be e to the negative 2 times 1 over square root of 5. The negative signs in this multiplication and this multiplication cancel out, plus e to the negative 2 times 2 over square root of 5. And unfortunately, the negative signs don't cancel out here, so this is actually going to be a negative minus. And this gives a final value for the directional derivative of negative 1 over the square root of 5 times e to the negative 2. So this value right here is exactly the directional derivative of this function, the function f, in the direction of the vector negative 1, 2 at the point 1, 1. So let's try and visualize this. We can visualize this in a number of different ways. The first way that you might think of is to do a plot of the three-dimensional function. So I use my Python code to do this, and I plotted a plane in that direction. So if you take this three-dimensional plot and you rotate it, you can see that there's a plane plotted at the point 1, 1 that's parallel to that direction. It's going along that direction. And essentially what this directional derivative is giving us is the slope of the trace of this surface along that plane in that direction. So this is one way of visualizing and kind of thinking about what the directional derivative is giving you. You're taking a trace in the direction of the graph of the function, and the trace in that direction is going to give you the rate of change in that direction. It's just kind of like what you would see if you were standing on this surface and directly walked in this direction. So along this plane on the surface, z equals f of x, y. Now a better way I think of thinking about it is always looking at the level curves or the density plot of your function. And I think that gives you a slightly clearer picture of what's going on. So the value that we just calculated is at the point 1, 1. So on both of these plots, let me open up the plot so you can see the plots here. So on both of these plots right here, you see we're at the point 1, 1. I plotted the gradient vector of the function in orange, so you can see the direction the gradient vector is pointing. And then I also plotted the unit vector going along this direction right here. So I plotted a vector going in the direction of the unit vector right here, which is in the vector along the vector -1, 2. I also plotted a line, right, that line that is kind of also going along in that direction. So that this number that we just calculated is exactly the rate of change that you would feel if you say, let's say this is a temperature field, if you were to move directly in this direction along this line at that point right there. It makes a lot of sense because if you're standing at this point and you move directly in this direction, you expect to feel a negative rate of change. The function's decreasing as you move in this direction. You know, darker red to lighter red. Or along here, if you think along the contour curves, the level curves, if you move in this direction, the function is going down. The value of the function is going down. So both of these plots very clearly visualize what exactly the directional derivative is giving us for this function right here. And you can hopefully clearly see the interpretation that basically the directional derivative doesn't depend on the path. It only depends on the direction in the function itself. So how quickly the function value itself is changing. So we can do a number of different things with the directional derivative, but we can also use this formula and use what we know about the dot product to get some general properties that hold for any functions. This is going to be properties of the directional derivative at any point for any function. And specifically what this tells us about also are properties of the gradient vector. At any point for a function. Specifically what we can do, and what we'll directly do, is use and ask, well, I guess what we'll do, start this out by doing, is asking what does the formula du of f at r naught in the direction u hat is equal to the gradient of f at r naught dotted with u hat. What does this formula tell us about the gradient vector? And it tells us a lot. We can actually use this to describe in general what direction the gradient vector is pointing, always. Now, what you should do is you want to recall the following property about the dot product. That was hopefully proven in a previous calculus course, but I can definitely go over this if you have questions on this. For any two vectors, A and B, so you have a vector A here and a vector B here that are at some angle theta. They're pointing in different directions, and the angle between them, we call it theta. Remember that the dot product has its primary definition as the algebraic definition. So it's just the multiplication of the components added together. This is what it is in 2D. In 3D, it's the multiplication of all three components added together, and so on and so forth. This is sometimes called the algebraic form of the dot product. But you hopefully saw in a previous calculus course that this is also, it can also be written in what's called its geometric form. So using this and using a little bit of geometry, specifically the law of cosines, the dot product can also be written as the magnitude or length of the vector A times the magnitude of the vector B times cosine of the angle between the two vectors. And this is sometimes called the geometric form of the dot product. So this is very, very important. It's important for a lot of different reasons, but specifically for us, we can directly apply this to the directional derivative. Instead of using the algebraic form of the dot product, we can use the geometric form of the dot product. And what we get when we do that, we apply that directly to our formula for the directional derivative, is that the directional derivative of a function in the direction u hat is exactly equal to the magnitude of the gradient vector at the point r0 times the magnitude of u hat times cosine of theta, where theta is the angle between the direction that we're looking for the directional derivative in the gradient vector. Because u hat is a unit vector, this is just equal to 1. And so another way of calculating the directional derivative at a point is to calculate the length of the gradient vector and multiply that value by cosine of theta. And this immediately tells us several interesting properties of the gradient vector. Cosine of theta is maximum. And remember, theta here is the angle between two vectors. So theta is between 0 and 180, or 0 and pi. So the maximum of the directional derivative, its maximum so this occurs when cosine of theta is equal to 1, or when theta is equal to 0. And this is interesting because it tells you that when theta equals 0, the directional derivative is maximum. That means that the gradient vector at the point r0 points along u hat, or you could say u hat points along the gradient vector. They're parallel, and u hat is pointing in the same direction. I guess I'll I'll rewrite that to be more specific. So the directional derivative is maximum when u hat points in the same direction as the gradient vector at r0, at the point r0. This is interesting because it's giving us exactly, it's telling us exactly that the gradient vector always points in the direction of fastest increase or maximum rate of change. If you look in the direction of the gradient vector, the directional derivative is maximum in that direction. For any function where the gradient vector exists, it is nice and smooth. The second thing we can show is that the minimum of this directional derivative occurs in some sense in the opposite scenario when cosine of theta is equal to -1. This happens when theta is equal to pi, or when u hat points in the opposite direction to the gradient vector at the point r0. So this is telling us that the minimum directional derivative occurs when you look in the opposite direction to the gradient vector. Or in the same way, you could say the negative of the gradient vector is when the function decreases most rapidly. And the third thing that this tells us is that the directional derivative is 0 when cosine of theta is equal to 0, where theta is equal to pi over 2, 90 degrees. And when this is the case, that means that u hat points perpendicular to the gradient vector at the point r0. And that's saying that the rate of change along level curves is equal to 0, which makes a lot of sense. If you are, say, moving along a level curve, you don't expect the value of the function to change because the level curve is, by definition, a set of points which the function maintains its value, a constant value. If we open up our plots from before, we can directly see this. So looking at the plots from the previous example, you see very clearly, and we'll look at these level curves right here, that this the directional derivative in this direction was negative because the function decreases if you move in this direction. But if you say move to a direction that is perpendicular to the gradient vector here is the orange vector. If you were to move in a direction perpendicular to that vector, the directional derivative would be 0. By the way, all of the vectors plotted on both of these plots here, the black vectors are the gradient vector at every given point. And you can see very clearly that the gradient vector at every point is pointing in the direction of fastest increase, or directly uphill, which is perpendicular to the level curves at any point. So this is it's very cool. We've just essentially proven using this directional derivative a fundamental property of the gradient vector for any function. So no matter what the function looks like, right, this is a property that we've shown. And what's nice about this is it also directly applies not just to functions of 2 variables, but functions of 3 variables, 4 variables. These properties are true regardless. So in 2D, we've seen that we have maybe a topographic map or of the level curves of a given function. Maybe it looks like this. Say that this point is a minimum of the function. So maybe the function's 5 here, 10 here, 15 here, 20 here, and 25 here, say. The gradient vector of this function at any point is going to be perpendicular to the level curves of this function and always pointing in the direction of fastest increase of the function, which, if this is a minimum point, always pointing away. Which, if you look at the previous plots, is exactly what happens when you think of the gradient vector at every single point. This also applies in 3D for level surfaces. So it's not that hard to visualize and to see in terms of level surfaces. In 3D, remember, we don't have level curves, but we have level surfaces. So let's say we have a minimum again here at we'll say 5. We have some level surface around this minimum, which corresponds to the value of 10, function value of 10. We have another level surface around this point, which corresponds to a level of 15. And then another level surface around this point. Which corresponds to a function value of 20. This is in 3D. So these are all level surfaces. But on this level surface, the outer level surface, the function value is 20. The next inner level surface, the function value is 15, and so on and so forth. The gradient vector can still be plotted. It's still going to satisfy all of the properties that we talked about before, where it's perpendicular to each one of these level surfaces at any point on the level surface. And it's always pointing in 3D now in the direction of fastest increase of our function. So if this is a minimum value of our function, the gradient vector is always pointing away from that minimum. So what we've just done is a very, very powerful tool, and it tells us exactly how the gradient vector behaves and how the gradient vector is directly applicable to understanding how a function is changing in any number of dimensions for any number of variables. So the last part of this lecture that we're going to consider, that I'll talk about, is going to be the following. Let's consider a very real-world example. We'll consider a topographical map of a mountain. And because I live in the Northeast, we'll consider what's called it's the highest mountain, or the tallest mountain in the Northeast. Which is not that tall compared to some of the mountains out west or in other parts of the world, but it's definitely a challenge to hike it. It's Mount Washington. So if we open up a topographical map of Mount Washington, we can see that it looks like exactly like this right here. And on this topographical map, you see a number of different trails. The summit of Mount Washington is right here. The parking lot of Mount Washington is right around over here. So when you drive there, you park over here. And there are a number of different trails to take. One of the main trails is called the Tuckerman Ravine Trail, and then it splits into the Tuckerman Ravine Trail and into then this other trail called Lionhead. Now, a year or so after grad school, I ended up going hiking in the springtime when there was still snow, but there was an avalanche warning in Tuckerman's Ravine. Tuckerman's Ravine is right here, and you see that it's kind of like a more gradual change. And this slope specifically right here, Tuckerman's Ravine, is very, very good for people will go snowboarding and skiing at all times of the winter, but also even into the spring because of the elevation. You still get snow there. So even though there was an avalanche warning that day, people were still snowboarding and skiing and whatnot. But we chose to take the Lion's Head Trail because we felt it might be a little bit safer. And about halfway up the Lionhead portion of the trail, right about here, you can see that there's initially a very steep incline. The level curves, these curves right here give the elevation at every given curve. And about halfway up the Lion's Head Trail, there's a nice kind of very, very gradual, almost flat section, which is actually perfect for stopping, resting a little bit, and taking a picture. So I ended up taking a really nice picture from this point right here on the Lion's Head Trail, and the view of the camera essentially encompasses about all of this right here. Then you can think of this as being a very nice viewpoint because you probably see a very, very you see all of Tuckerman's Ravine, and it's like a steep slope right here kind of going up. So all of this stuff is at a higher elevation than this point right here, but you can still get a very nice picture of a very, very nice cliff. So if we go through and look at the picture, you can see this is exactly what we see. So there's me. I'm standing right at this point marked on this map, the map right here. And you can see in the picture that you get this very nice view of both Tuckerman's Ravine. And if you look close enough in the picture, you can see trails right here where people are skiing and snowboarding. So if you look close enough right there, there's someone snowboarding down the trail right here, down the ravine trail. So I thought this was a nice way to end the lecture and to show how you might want to use the directional derivative in real life. You could say, take a map, and just looking at the map, choose the area that you'd get the best photo from. There are many other applications, but this is one very kind of personal and very cool application that I wanted to show. Thank you very much for listening to the lecture today. If you have any questions, let me know, and I hope you learned something. But have a great day.